This is lesson 10.4. Today we're going to continue talking about factoring and multiplying, but we're going to talk about something called conjugate pairs. So your aim today is that you can recognize conjugate binomials, I'm going to talk about what the word conjugate means, and factor them based on the rules of conjugate pairs. So we're going to talk about this word conjugate and how to factor and multiply using them. This is actually a pretty easy lesson once you see the pattern. It's a pretty, I would always rather have a conjugate pair because you'll see a really cool pattern. So there are a number of different types of factoring techniques, but each one of them boils down to reversing a product. So we're going to begin the lesson today by looking at products of conjugate binomials, or binomials in the form of a plus b and a minus b. So this right here, that is a conjugate pair. It's always the same number and then plus another number, then the same number minus that same number. So a plus b, a minus b. So if you look at exercise 1 letter A, do you see how they both have an x, then they both have a 5, and they're completely identical except one is plus and one is minus. That is a conjugate pair. Okay? Same thing with b. Always have the first the same, the second the same, and the only thing different is one is plus, one is minus. This is a conjugate pair. So what we're going to do in exercise 1 is find the products of all of these and then see if we can find a pattern. So let's start. I'm going to make my box. On the top of my box I'll put the x plus 5, and on the side of my box I'll put x minus 5. X times x is x squared, 5 times x is 5x, 5 times a of 5 times x is negative 5x, and negative 5 times 5 is negative 25. Now, something very interesting is going to happen here. Notice my like terms are negative 5x and 5x. Well, what happens to those two terms when you add them together? What's negative 5x plus 5x? It's 0. So these two terms, they cancel out to 0. So I'm really just left with the x squared and the minus 25, because these go to 0. Okay? I could write it out and show you here. I have x squared plus 5x minus 5x minus 25. And you can see here when I combine like terms, I end up with x squared minus 25. Okay? So those two middle terms cancel out to 0, and I'm just left with x squared minus 25. So here's where we're going to start to see our pattern. Okay? I'm going to go ahead and do this letter C. 4x plus 1 and 4x minus 1. We're going to multiply like normal. 4x times 4x is 16x squared. 4x times 1 is 4x. 4x times negative 1 is negative 4x. And negative 1 times positive 1 is negative 1. Notice the same thing happened here. The two numbers on the inside are like terms, negative 4 plus 4, that cancels out to 0 as well, so those are gone, and I'm just left with 16x squared minus 1. Okay? So we're starting to see something interesting here. Okay? So I'll do B. Actually, let's do E here, so we can nail this pattern down finally. If you can start to guess the pattern, I would. I'm going to put the 2x plus 3 here and 2x minus 3 here. 2x times 2x is 4x squared. 3 times 2x is 6x. And 2x times negative 3 is negative 6x. 3 times negative 3 is negative 9. Again, notice my two like terms are opposites of each other. 6x and negative 6x. So they cancel out, and I'm just left with 4x squared minus 9. So let's take a look at our pattern, okay, before we go on to the other three. Notice my first two terms, x and x. What was my first in my answer? X squared. What are my last two terms? 5 and 5. What's 5 squared? 25. Does the same pattern hold true? 4x and 4x. What's 4x squared? 16x squared. And what's 1 squared? 1. Same thing here. 2x and 2x. What is 2x squared? 4x. 3 and 3. What's 3 squared? 9. So this is our pattern. Okay, the pattern is you square A and square B and subtract. So based on this definition, where I'm going to square A and square B, my answer to B should be x squared minus 4. Because I have x and x, that's x squared, and 2 to get x squared minus 4. Well, let's see if I get x squared minus 4 when I try and do this out the long way. So let's do it the long way. X minus 2 and x plus 2. X times x is x squared. Negative 2 times x is negative 2x. And 2 times x is 2x. And 2 times negative 2 is negative 4. Again, I get 2x minus 2x, which cancels out to 0. So I do get that answer of x squared minus 4 that I could predict with my pattern. Okay? So therefore, letter F, I'm not even going to do the work for letter F. I'm just going to notice that, okay, I have 5x, so I'm going to square that, minus, in fact, let me put my minus in color, minus, because it's always a subtraction sign with this pattern. Notice it's always been a minus sign in all of these answers. Minus this 2y squared. So when I simplify, I'm going to get 25, because that's the 5 squared, x squared, minus 4y squared. So I don't have to do any work for this problem. That's why conjugate pairs are so nice. You don't have to do any work. You just memorize to square the first two numbers and subtract them, and that's your answer. Okay, conjugate pairs are really nice for that reason. So that means the answer to this, well, would be x squared minus y squared. The x and the y. You just subtract the two squares. So the formal definition of this is in this box right here. Okay, what we should see is that if we multiply conjugates, if we multiply them, opposites always cancel, like we saw, and instead of getting our expected trinomial, we get the binomial. So here's the actual definition right here. A plus b times a minus b, that's the conjugate, is always going to be a squared minus b squared. Always, forever. Okay, if you have the same number and as the first number, and the same second number, and their conjugates, they will always follow this pattern. So let's try to do these quickly, right? Number 1, I have my first number is x, so it's going to be x squared, minus my second number is 6 squared, so I'm going to get x squared minus 36. Okay? How about I try e? My first number is 6, so I get 6 squared, minus my second number is 5y, so 5y squared. And when I simplify this, 6 squared is 36 minus 25y squared. Okay? Let me do letter C, and then I want you to try to do a couple on your own. So my first is 2x, so that's 2x squared. My second term is 7y, so minus 7y squared. And I simplify. This becomes 2x squared minus 14y squared. Okay. Go ahead and pause and try B, D, and F on your own. Alright, I hope you tried these on your own because that's the best way to learn. So for letter B, you should square the 5x and then minus squaring the 2. So you should get 25x squared minus 4 as your answer for B. Okay. And I just noticed that I made a mistake over here on this 14. What did I do wrong? Look what I did. Look at this mistake that I've called out on you guys. What did I do? I did 7 times 2. What was I supposed to do? I was supposed to do 7 squared. So that would give me a different answer. That's going to give me 4x squared minus 49. See how easy it is to make a mistake? But I caught it. Alright. Let's hope I don't do that again. Alright, letter D. My first number is 4, so I have 4 squared minus my second number squared, which is x. So I get 16 minus x squared. Okay. And finally for F, my first term is 10x, so I have 10x squared minus my second term, which is 4y. I'm going to square that. I'm going to simplify to get 100x squared minus 16y squared. Okay, so this is our easy way of multiplying conjugates. This only works on conjugate pairs. It does not work any other time. Okay, it's got to be a conjugate pair. So be careful with that. So the other thing that this lets us do, besides just multiplying easy, this allows us to factor easy. Okay, remember, factoring is the reverse of multiplication. So we now should be able to reverse this multiplication in order to rewrite the expressions that are called the difference of perfect squares. So now we're going to go backwards. So exercise 3 has, so see we have A has 8x minus 81. Do you see how that answer looks very similar to letter A, this x squared minus 36? Or this 16 minus x squared? You have a difference, so you have this subtraction, and on one of them is something that can be squared, and the other one is something that can be squared. So all we have to do is recognize that this is a difference of perfect squares. Okay, so I can rewrite this as x squared minus 9 squared, because isn't 9 squared 81? And then, because I remember this pattern, I know that this would become a complex conjugate, or sorry, not complex conjugate, but a conjugate pair of x plus 9 times x minus 9. So this is a little bit harder because you have to think backwards, right? So let's take a look at B. How can we take letter B and put it back into a difference of squares? So 9x squared is the same as this 3x squared, and 4 can be reduced to 2 squared. So you're going to try and put both of the numbers in terms of something squared. Then you can see that, oh, okay, it's going to be 3x plus 2 times 3x minus 2, right? You're looking at what that term is. The first term is 3x, the second term is 2. So that reverses it into your conjugate pair. Okay? A little bit tricky and does require some practice to recognize. Okay? So letter C. Alright, I can turn the 25 into 5 squared and leave that as y squared. And now I have 5 plus y and 5 minus y as my conjugate pairs. Okay? Remember, I want this difference of perfect squares. Once both of the things have the squares on them, then you can make your multiplication problem. Okay? But like, for example, letter D here, I can't say 4x plus 81y times 4x minus 81y. I can't do that. Okay? Because this 4 doesn't have a 2 above it. So I can't do this. Instead, I'm going to take this 4 and turn it into 2 squared. And I'm going to take the 81 and turn it into a 9 squared. Okay, I'm basically reversing squaring that. Now I can do 2x plus 9y times 2x minus 9y. Now that I have both of them as squares. Okay. Letter E, if you're unsure of some of these squares, you can always put it in your calculator as this. What is the square root of 121? Well, the square root of 121 is 11. So if you're not sure if something is a square or a perfect square, usually, these are our perfect squares, what I'm listing here. All of these numbers have, a perfect square. 4 is 2 times 2, 9 is 3 times 3, so forth and so on. But when you get to those big numbers, sometimes you forget. So it's not a big deal. Use your calculator to check. So I know the square root of 121 is 11. So I can simplify this to 11x squared. And I can also simplify this 1 in a weird way to 1 squared. Because isn't 1 squared the same thing as 1? So when I write it this way, I can suddenly see that I can do 11x minus 1 times 11x plus 1 as my factored expression. Okay? This one right here I would say is the trickiest one. Because you have to recognize that what 121 and 1 is as perfect squares. And sometimes that can be really hard. And finally, the last one, like we said, we can rewrite 1 as 1 squared, and this can be 2x parentheses squared to get 1 minus 2x times 1 plus 2x. Okay, and this might be a good lesson that you might need to ask for help on. So if I've said anything that you've gotten lost on, or you're like, Miss, I don't know what you're doing in any of this section, this is where you'd mark it on your paper and come see me or Ms. Vasquez or Ms. Sammer and say, can you explain this? Okay? All right, let's take a look at the last exercise and try and remember this idea that when we factor something, we're really just rewriting an expression. We're not solving anything, we're not finding x, we're just rewriting the expression in a form that might look different, but really is equivalent to the original. And this is going to have a really good meaning later in the units we have when we come to solve. So we are going to do this for a reason, this factoring. So let's take a look at making something equivalent here. So let's take a look at the binomial x squared minus 9. Amelia believes that x squared minus 9 can be factored into this, x plus 1 times x minus 9. So she thinks that this is the correct factorization of this. While her friend Isabel, so that's what Amelia thinks, and Isabel believes that it's factored as this. Okay? Fill out the table below to develop evidence as to who is correct. Use technology in your calculator to help if you'd like to. So we're going to go ahead and we're going to simplify this. The best way to do this is to plug this into a graphing section on the calculator and then get a table, because it might take you a long time to do this in your head. Okay, so I'm going to go ahead and write Amelia above this. So this is what Amelia thinks, and the other section is what Isabel thinks. So the original equation is this one. So when I plug in 0 squared minus 9, I get negative 9. When I plug 1 squared minus 9, I get negative 8. If I do 2 squared minus 9, I get negative 5. And 3 squared minus 9 gives me 0. Okay? So these are my values for when I plug in 0 to my equation. So the idea is, well, whoever's right will have these same values when they plug into their new expression. So let's try Amelia first. So Amelia is saying, let's plug this in 0 plus 1 times 0 minus 9. That's going to give me 1 times negative 9. I get negative 9. So the first one checks out. How about the second one? 1 plus 1 times 1 minus 9, I get 2 times negative 8, I get negative 16. And right there I can see that Amelia might be wrong, because what number should she have gotten? She should have gotten an 8, and what'd she get? A negative 16. So I'm going to stop there and see if Isabel's right. So Isabel, we're going to plug in 0 minus 3, 0 plus 3. And that's going to give me negative 3 times positive 3, which does give me a negative 9. So she's right for the first one. Let's plug in 1. 1 minus 3 times 1 plus 3. That gives me negative 2 times 4, which gives me negative 8. So far, so good. The next one, 2 minus 3 times 2 plus 3. That's going to be negative 1 times 5, which gives me negative 5. She's doing good so far. And, you know, we don't really have to check the last one. We can already see that it's working, but let's just prove it one last time. 3 minus 3 times 3 plus 3. Well, 3 minus 3 is 0, and 3 plus 3 is 6, and anything times 0 is going to be 0. So Isabel is correct. And notice that she used the pattern. What'd she do? X squared minus 9, she did, if we're simplifying this, she's going to take x. This is like saying x squared minus 3 squared to get that x minus 3, x plus 3 very easily. Okay, so she's using that pattern. Amelia thought that it could be 1 times 9, because if you multiply 1 and 9, you do get the negative 9 that's in the original equation. But if you were to multiply this x plus 1 out, you'll see what happens. So let's show that. Let's do Amelia and show what happens when you multiply hers out. Right? If I multiply hers out and do x plus 1 and x minus 9, x times x is x squared, 1 times x is x, x times negative 9 is negative 9x, and 1 times negative 9 is negative 9. I get x squared plus x minus 9x minus 9, and when I combine these two middle terms together, I get a negative 8x. And this is not what my original equation was. My original equation was this x squared minus 9. So Amelia's wrong. She's wrong in the table, and she's wrong when she multiplies it out. But Isabel, when we multiply Isabel out, x minus 3 and x plus 3, we're going to see it canceling out that middle term. X times x is x squared. Negative 3 times x is negative 3x. 3 times x is 3x. And negative 3 times positive 3 is a negative 9. Look at the middle two terms. They're opposites, so they cancel out to 0. And I'm left with x squared minus 9, which was my original equation. Okay? So there's a lot of ways we can show equivalency. There's a lot of ways we can multiply and factor different expressions. Okay? This might be the first time you've done conjugate pairs, so I encourage you to seek help, especially because the answer key is not going to have work on it. Okay? So good luck, and please ask lots of questions.